In our series on cycling biomechanics is another review article, a recent article in 2020 by Turpin and Watier, titled Cycling Biomechanics and Its Relationship to Performance. I positioned this paper as number 2 in the series here because I didn't want to give you the impression from the previous lecture, the first lecture in cycling, where I argued that cycling is biomechanically simpler than running. I didn't want to give you the impression then that cycling biomechanics are simple in an absolute sense. I think they're simpler than running biomechanics in terms of the biomechanics of the movement of the athlete's body due to those constraints that you have in cycling that aren't present in running that I went over last time. But in an absolute sense, cycling biomechanics are not simple, and especially when coupled with the mechanics of the bike that kind of interact with the rider's biomechanics there, the overall mechanics involved in the whole system become quite complicated. And so this is an article that focuses a little bit more on specific technical aspects of biomechanics in cycling. It's still a review article. It's still summarizing a wide range of issues, not covering like a specific original research article type issue, but it's a little bit more focused than the previous article on some specific elements of biomechanics as they relate to performance in cycling. So a few things that I wanted to emphasize here in this paper. At the top of section 2, they give what I think is a real nice kind of center of mass level definition of performance from the perspective of mechanics in cycling. In cycling, you have the bike and you have the rider of the bike, and those two things together, you plus the bike, will have a combined mass m, and your goal is typically to translate that system, the bike plus rider system, or that mass m of the bike plus the rider, at a certain velocity v, at the fastest velocity v possible. Okay? We can compute how much kinetic energy it takes to translate the bike at that speed. It'd be 1/2 times the mass of the bike plus the rider times the square of that velocity. That's how much kinetic energy you would need for the bike to travel at that velocity. If you're in a vacuum, like a place with no air resistance, and if you have a idealized frictionless bike with no friction between the parts on the bike, and if you have infinitely stiff tires that don't deform at all, and if you're traveling over level ground, then you could just pedal for a bit and accelerate your bike up to that velocity, and then you could stop pedaling and the bike would just infinitely travel at that velocity until you did something else to stop it or you ran into something. In reality, that's not the case. In reality, I would accelerate my bike up to this velocity, and if I stopped pedaling, then the bike would eventually slow down and come to a stop and lose all that kinetic energy. Why? Because remember, there's these sources of resistance in real cycling. There's air resistance. There's rolling resistance. There's some friction in the parts of the bike, like the friction between the chain and the gears and friction of really any moving part on the bike. And then there's also, when I'm in the case of going uphill, there's gravitational resistance. All of these sources of resistance here can be manifest as forces that act on the bike or on the rider that dissipate away some of this kinetic energy. Okay? And so this is why when I accelerate the bike up to a certain velocity from rest, if I then stop pedaling, the bike will stop moving at that velocity and will eventually slow down. To keep it moving steadily at that velocity, I have to be continuously, with my body and my biomechanics, continuously putting more mechanical energy into the bike riders, into the bicycle, in order to keep it at this velocity and to account for the energy, the fraction of this kinetic energy that's being sucked away by these sources of resistance here. Okay? I do that by pressing my feet into the pedals and turning the crank, and through that generating what's called crank power. Crank power is a real common metric that's tracked in cycling. A lot of serious cyclists will have devices that you can attach to the bike or special like instrumented pedals that will measure the crank power that they're producing. It's a metric that's used for tracking training. It's a metric that's used for assessing pedaling technique. It's a metric that's used for assessing performance. It's a very common and versatile metric for training and for performance in high-level cycling or in serious cycling athletes. What is this crank power exactly? Well, this is what's shown in figure 1 of this paper. Here's my simple model of the cyclist's leg, my hip, my knee, my ankle, and my foot. My foot connects to the crank, which is this little line here going towards the center of that circle. I press on the crank with my foot, and it rotates around this circular path here, just like I was demonstrating when I was rotating my foot around that circular path in the previous video when clipped into my bike. Okay? So that force that you're pressing on the pedal with to rotate it will generate an angular force around this axis of rotation that rotates the crank arm, and it will be rotating it at a certain velocity. Okay? So crank power here is mathematically equal to the crank torque times the crank angular velocity. Okay? So basically how hard you're pushing on the crank times the velocity at which you're rotating the crank, the product of those two things gives you the crank power. Crank power is an important metric because that crank power is what is being pumped into the bike energy-wise to increase or maintain this kinetic energy. Okay, so your crank power can translate pretty much directly into the kinetic energy of the bike and through that the velocity of the bike. And so this mechanically, at least at kind of a superficial level, is how you power the bike, is how you generate the power that the bike needs to travel at a certain velocity from an energetic perspective. Okay. Now, two terms that they emphasize in this paper that I'm going to emphasize here that relate to the production of crank power and the performance in cycling. And these terms are important in all types of cycling. The first one here, mechanical effectiveness, I would say this is a factor in both long distance and short distance cycling. Like long distance races like you see in Tour de France where they're on the bike for hours and hours each day, and also the shorter distance races that you often see in the Olympics where it's like the sprints that are much shorter cycling races. Mechanical effectiveness is important for both of those. Gross efficiency is not trivial or negligible for sprint cycling, but is much more of a factor in long distance and endurance cycling. So they don't really speak to it all that directly in the paper, but the gross efficiency element is probably more of a factor in long distance cycling for sure than it is in sprint cycling. And these two factors are related to each other and kind of have some overlap in terms of how they influence each other. So what are these exactly? What is mechanical effectiveness and what is gross efficiency? Mechanical effectiveness is what they're getting at here in figure 1 with some examples. They abbreviated ME here for mechanical effectiveness. I think they use that pretty consistently throughout the paper. ME here is a function of the force vector that you produce with your foot in pressing on the pedal and turning the crank. Mechanical effectiveness can vary from 0 to 1. It can actually vary from -1 to 1, but negative mechanical effectiveness is basically pedaling backwards, which you won't probably want to do most of the time. So for an athlete endeavoring to like pedal or turn the crank forward and travel forward, mechanical effectiveness in theory will vary from 0 to 1. In practice, if you measure it in like actual cycling with good technique cyclists and lesser good technique cyclists and bad technique cyclists, in practice it'll vary typically from like 0.1 to 0.8, maybe 0.9 or so. You can train people to get it to be close to 1 or really close to 1, but generally that's not effective for performance, as we'll cover a little bit later. So what is this mechanical effectiveness ratio exactly? This is the ratio of the component of the force that you apply on the pedal that is tangent to the rotation of the pedal versus not tangent to the rotation of the pedal. And what do I mean by that exactly? I'm going to go down to my basement here and show you a video there of what I mean exactly by forces that are tangent to the circular path of the pedal / crank and forces that are not tangent to that circular path. Give me a second here to pull up my QuickTime. And start a new recording. Okay, let's make that screen a little bigger. And get the crank in there. Okay. So let's suppose my crank is up here in what's called the top dead center position, where it's pointing vertically straight up and down or pretty close. I probably don't have it exact, but pretty close. If I want to turn the crank, there's only one direction of force that I could apply to the crank with my foot that would result in it turning. It would be a force pointed straight horizontally in this direction. Okay? That's the only direction of force that I could apply to the crank that would actually turn it around that circular arc. Any other force that I apply to this crank that's in any other direction is essentially wasted in terms of actually turning the pedal, right? If I apply a force upward, doesn't matter how big that force is, it doesn't turn the crank. If I apply a force downward, doesn't matter how big that force is, it doesn't turn the crank. Okay? So in reality, the force that I'm probably, when I'm actually pedaling, applying to that crank will have a component in the horizontal direction and a component in the downward direction. The component in the horizontal direction is tangent to this circle, meaning that if you were to draw a line in that same direction, it would only intersect that circle one time. It would only intersect it at the top here. Okay, that's what it means for the force to be tangent to that circular arc there. Compare that to the force that would point downward. If I was like pressing straight down on the pedal, that would run through the crank here and would intersect it twice. It would intersect it once down here at the top and again down here at the bottom. So it's not tangent to that crank path. Whereas the force in this horizontal direction is tangent to that crank. It would only touch, or to that circular arc, it would only touch it once. Another way of thinking about it is that if you take the tangent force and draw a line perpendicular to it, it'll form a 90-degree angle there between the direction of the force and the moment arm for that force to the axis of rotation there about the crank. That's the force that's tangent to that axis of rotation there, a tangent to this circular path. So producing a horizontal force on the pedal there will effectively rotate the crank when it's in that position, and producing a vertical force will not effectively rotate the crank when it's in that position. I could press here downward all day long and it won't rotate the crank at all. It's got to be a horizontal force to do that. So in reality, when I've got my crank in this position, when I'm actually pedaling, like if I'm pedaling around and you snapped your fingers and froze me in this position, in reality, the force that I'm applying to the crank at that time will probably have a component in both directions there. Part of that force will be directed horizontally, and part of that force will be directed downward. So for the maximum mechanical effectiveness, or maximum ME, like ME equal to 1, in that position, I would want all of my force there to be directed horizontally, and none of it to be directed downward. Okay? That would give me the maximum mechanical effectiveness. Similarly, if I'm over here at a crank angle of 90 degrees, then my tangent force would be pointed downward in this direction. That would give me the most mechanical effectiveness. The least mechanical effectiveness would be a force horizontally in this direction, right? I could go to this other side here, and I can push on the crank horizontally from that direction all day long with all my might, and I'm not going to rotate the crank, right? It's only the force tangent to the circular travel path of that crank that's going to rotate it in that position. Okay? So the notion of mechanical effectiveness here in pedaling is that as you are rotating the crank around this circular arc with the forces that you're producing on the pedal with your feet as you're pressing on it, ideally you want to be producing forces that have a lot of mechanical effectiveness, that have a force direction that is tangent, or as close as tangent as possible, to the path here of the circular arc of the crank as can be. Okay? So you want to be producing forces that are effectively rotating the crank and not producing a lot of forces that are not effectively rotating the crank. So lots of force that is in the tangent direction to the circular arc here, and not much force that's not in the tangent direction, that's going back along the direction of the crank and is not effectively rotating the crank. Okay? So that notion of mechanical effectiveness is essentially that ratio there. If a pedaling technique has all of its force in the direction that is effectively rotating the crank or tangent to the crank, then that is a mechanical effectiveness of 1, and if it's a ratio of forces or a direction of forces that has no force in the direction that's effectively rotating the crank, then that would be a mechanical effectiveness of 0. Okay? So you might think that the best pedalers in the world are like really skilled, really talented, really effective cyclists would have a mechanical effectiveness of 1 or close to 1, right? As they're moving the crank in the direction around the pedal here, they would all, or around the circular arc here, they would be producing forces that kind of always look like this F2 arrow here and never look like this F1 arrow, or the big component to the force that's kind of wasted and is not effectively helping to rotate the crank. That is actually not what you really see in even any cyclist really, or especially in skilled cyclists. Even like really talented, really experienced, really efficient cyclists do not have mechanical effectiveness values of their pedaling technique that are all that close to 1. Like I mentioned before, you might see like 0.8, maybe like 0.85. Those would be pretty high mechanical effectiveness values even for a good cyclist. But their actual force vectors as they're pedaling look more like this, where you can see here at any point along this direction of travel, their force vectors have substantial components that are not directed in the tangent direction. Okay, so they're producing a lot of force here that is not effectively rotating the crank. Okay, so why is that? What's going on there? Why does it seem that are they like being really wasteful here? Could they optimize their technique and be even faster and even more efficient if they learned a thing or two about biomechanics here? Likely not. What's typically going on here is that the amount of torque, if I go back to my definition of crank power here, the amount of torque that you produce on the crank there is not purely going to be a function of the direction of that force. It's also going to be a function of the magnitude of that force. Okay? So for example, even though this force here, if here I'm looking at figure 1b, if that's not obvious, even though this force here, F1, is much less mechanically effective than this force F2, and why am I saying that's less mechanically effective? Force F2 is only purely directed in the direction tangent to the circular arc here. Okay? Force F1 has a mechanical effectiveness much less than 1, and so it's because it's not purely directed in the direction tangent to that arc here. Okay? But notice here how much bigger force F1 is than in force F2. So force F1, if I were to split it up into a component that's tangent, so like that, and then a component that's not tangent, like that, the component that's tangent in force F1 here is much, much bigger than this force F2 here. Okay? So force F1, even though it's less mechanically effective, there's a lot of like lateral, quote unquote, wasted force here, is actually going to produce more torque about the crank here, and if we're able to maintain the velocity, more power about the crank here, because it's just simply producing a much bigger force, and it's going to have a much larger magnitude of force in the tangent direction, even though it's quote-unquote wasting some of that force horizontally here in the non-tangent direction. Okay? So that's generally what you see over here when you look at like real forces produced by real cyclists. And you look at these and say, in a lot of these places, it looks like they're not real close to tangent at all with their force vector. They're wasting a lot of force there. Yeah, they might be, but they may be producing magnitudes of force in the tangent direction that are much bigger than they could produce if they were only trying to produce all of their force in the tangent direction, if that makes sense. The reason why you might want to kind of quote-unquote waste some force here that's not in a mechanically effective direction is that in order to get the forces pointing always purely in the tangent direction, you might have to do like really weird postures of your joints here that aren't comfortable or you aren't familiar with. You might have to stretch the muscles at places on their force length curve or on velocities on their force velocity curve that aren't efficient for using those muscles and producing the forces needed to get your pedal force vector here pointed in the right direction. So it seems like there's factors at play here in terms of performance in cycling that go beyond mechanical effectiveness. Okay? So I don't mean to like just poo-poo completely on mechanical effectiveness here. This is an important thing to look at. It is something that you can measure on like a cyclist with instrumented pedals, and if it's like 0.1, 0.2, then that person's pedaling technique kind of sucks and they probably need to work on it. But if it's like 0.6, 0.7, should you necessarily try to make it 0.8, 0.9? If the cyclist isn't really having any struggles, then that may not necessarily be a good thing. They may already be pretty close to what's ideal for them, even if what they're doing is not theoretically optimal from a mechanical effectiveness perspective. Okay, so if it's not purely mechanical effectiveness, what else is it that matters for cycling performance? That's where this notion of gross efficiency comes in. Efficiency in general, in science or in engineering or just in general, is basically output over input. You can also think of it more broadly as the payoff that you get for the cost that you paid for it, right? So in cycling, this would be typically defined as the crank power as my output, because that's what's going to translate most directly to my velocity of my bike, divided by the metabolic rate, or the rate of metabolic energy expenditure of the cyclist. Okay? This efficiency here for sprinting, again, this isn't that big of a factor, right? For sprinting, I just want to crank out all the power that I possibly can as quick as I possibly can. Okay? Whether it has a high metabolic rate or not, I don't really care that much, because it's such a short race, I'm probably not going to be metabolically limited by how quickly I'm consuming energy. Typically in sprinting, I want a high metabolic rate. I want to consume energy really fast so that I can produce a lot of power, and that's okay because it's a short enough race. I'm probably not going to like exhaust myself. I probably won't be limited by the availability of my metabolic energy. In a longer race, in like a long distance cycling race, and these are typically like hours in length, very long races, then this becomes critical, right? You want to produce a lot of crank power, so you want a big number here on the top, but if it means you have too big of a number here on the bottom, then you're going to burn up your energy too fast, and you won't be able to sustain that power output. You won't be able to sustain that velocity associated with that power output. You'll have to slow down and produce less power and less velocity, and you may not even be able to rest and recover and get back up to the velocity that you want. Okay? So modulating your efficiency here, producing the necessary crank power, but doing it efficiently, doing it with a reasonable or a maintainable metabolic rate is a key factor here for performance in endurance cycling. And so that's why it becomes important both for performance in terms of speed, in doing things like adjusting your posture to minimize air resistance. That helps directly with performance in terms of reducing air resistance and increasing velocity, but it also helps to allow you to maintain a certain crank power with a lower metabolic rate, because you don't have so much air resistance to pedal against to maintain that velocity. Okay? Similar story here for rolling resistance, right? Why would you want to like crank up the tires in terms of the tire pressure to reduce rolling resistance? Well, it'll help with velocity, right? But it'll also help with how much metabolic energy you have to expend to go at a certain velocity, how much rolling resistance you have to overcome to move at a certain velocity. Okay, so these things are kind of closely related here, the notion of sources of resistance and crank power and the metabolic energy you have to produce with your body to supply a certain crank power and move the bike at a certain velocity. Okay. Other little bit that they touched on here that I wanted to cover was the notion of the posture of the cyclist in terms of whether you're seated on the bike or whether you're standing up on the bike. And so you'll see this often in cycling, where a lot of the time they will be sitting down on the bike, like with their butt on the seat of the bike. But then at certain times, especially when they're like trying to accelerate quickly or when they're trying to climb a substantial hill, you will see the cyclist stand up off of the seat and basically be standing up on the pedals and kind of stomping down on the pedals and not seated. So still clipped into the bike, still pedaling the bike, but doing it while they're in what's called a standing position or standing up on the pedals, not seated on the bike. Why do they tend to do that when they want to go uphill? That's probably the most common time you see a cyclist doing that. When you're going uphill, that's when this gravitational resistance becomes substantial. Okay, then I have gravity here sucking kinetic energy away from me with every second that I'm moving up that hill. And so to keep moving up the hill at a certain velocity, I need to supply additional power to overcome the gravitational losses there, the potential energy losses due to moving up the hill. In other words, as I go up the hill, I have to keep adjusting my total energy of my bike to keep adding potential energy into the system by producing more power of the crank there. So here I not just have to keep up my kinetic energy, I also have to keep continually adding additional power to keep adding additional potential energy to the bike rider system here. And so that's why traveling uphill is difficult in cycling from a mechanical energy perspective. You have gravity here, meaning you have to produce not just kinetic energy, but also potential energy to keep moving upwards and keep raising your center of mass up the hill. So why do you often see cyclists stand up in the pedals? You'd think, well, it must have something to do with efficiency here, right? It must make me able to produce more crank power and or ideally do it with a lower metabolic rate. Generally, what's happening there when a cyclist stands up is, remember when I was given the video demonstrating me seating on the bike last time, the bike seat was touching me, it was touching my bum, and that was what was carrying the weight or bearing the majority of the weight of my body. Okay? When I stand up, then that weight, the weight of my body, my trunk and my legs and everything basically, is now no longer borne by the seat, but that weight is now borne by the pedals. And so when I'm doing kind of the downstroke part, when I'm doing the downstroke part of pedaling here, like when I'm going from top dead center down to like the bottom of my pedal stroke here, which is where most of the power in your pedal stroke comes from, then I'm not getting a contribution just from my muscles here, extending my joints and pressing on that pedal and moving it downward. I'm also getting a contribution from gravity, from my body weight being pulled down due to gravity and moving the whole thing down there from gravity. Okay? There's also an argument that can be made, and the paper touches on this briefly, that when you're standing up, you could like grab onto the pedal grab onto the handlebar on the side that you're pedaling on and kind of grip that and use that to like really kind of torque down on the pedal and really kind of pull your whole body into the pedal. That's a common thing you'll hear in like cycling coaching. Like you'll see coaches of cyclists kind of critiquing their form if they're like using their arms too much when they're climbing and not using their legs enough and things like that. But there's kind of a general presumption in cycling that when you stand up and if you kind of crank with your upper body on the handlebars while you're standing, that you can get some of that power that you're generating with your upper body to transfer like into your hips and into your legs and get extra power on the crank. In measurements of such things, that's true to some extent. You can seem to get maybe a few percentage points, like maybe 5% extra power or so when you stand up and really crank and really push with your arms there as well as with your legs. Whether that's a good thing or not is a little bit of like a chicken egg argument. Like, is the extra power worth the extra metabolic energy that you're consuming by using those upper body muscles as well? In some cases it might be, like on a short hill or towards the end where you're kind of in a sprint and just really want to get over the top and really want to finish, probably a good thing. If it's a really long hill and it's going to be quite an effort to get up it, maybe you don't want to be spending that extra energy to get a little bit of extra power. So it all kind of boils down to, again here, back to gross efficiency and the power that you get out versus the metabolic energy that you put in. Is the extra metabolic rate that you're consuming, the extra metabolic energy you're consuming, is this giving you more power? Hopefully it is, but is it giving you enough to have your efficiency stay the same or even improve, or is it making your efficiency worse? On a short effort, especially if it's near the end of the race and you don't have to sustain it for much longer, then you may just care about power. On a long effort or an effort in the middle of the race where you finish it and you still have to keep going for a while, then maybe efficiency rather than just absolute crank power is the factor to consider there. Okay. So no simple answers on it, and this is why cycling is difficult and is a very tactical sport at times, but just a variety of the factors you have to consider there. Do you want to stand up and really crank with your arms? That may get you some extra power, but is that extra 5% of power enough to justify the extra energy cost and possibly a drop in efficiency? Sometimes not. Kind of depends on the situation. Okay, that is it for now. We will see you next time. Have a good weekend.